This is what actually to be designed. We have already discussed this in our previous class. Now you need to design a memory system for 8086 microprocessor. This is for 8086 microprocessor. I have also told you about even and odd addressing during my last class. I don't repeat in every class. You are supposed to know it to understand this class. Otherwise, you will not be able to understand anything in this class. The design says you have to interface a memory to 8086 microprocessor. You have to interface 4K ROM and 8K RAM. Okay? The 4K ROM starting address is 0000H. 8K starting address is 800H. But the chips available is 2716 and 6116. The chips available are 2716 and 6116. Okay, can you tell me what is the capacity of chip 2716?
2 kilobytes.
It is 2 kilobytes. What is the capacity of chip 6116? 2 kilobytes. Right? Your chips are 2 kilobytes. So definitely you have to put multiple number of chips. Right? Okay. So memory requirement is 4K. You know how many 2716 are required? 2. And how much RAM is required? 4. Okay. So this is what done in this. And I hope you remember this is what your memory tree is. You need 4K memory, but available memory is 2K. You need to go for 2, right? In that there will be 2K even and there will be 2K odd. Okay, I told you about this, right? And also I have told you about starting and ending address. Can you tell me if the starting address is of ROM 4K ROM is 0000, what will be the ending address? I have already told you about this. Starting address of this will be 0000H. What will the ending address?
00.
00H. In that, all even address will be coming here and all odd address will be coming to the next 2K. Right? Similarly, you have another 8K RAM. What is the starting address? Starting address is 0800H. Can you tell me what is the ending address? 09F. Okay. Now, once again, what is available? What is available is 2K chip, right? So in memory tree, once again divide it into 2 4K chips. This 2 4K chips once again divided into even and odd. So you will have this will be ROM even, this will be ROM odd. Okay, now see here, this will be RAM 1, this will be RAM 2, right? So this 2K chip will have all even addresses of this 4K. This will have all odd addresses of this 4K. Similarly, this will have all even addresses of 4K. This will have all odd addresses of 4K. Can you tell me what is the address range of this 4K? What is the address range of this 4K? Starting from 08000H to 08F. What is the address range of this? 09000H to 09FFH. So in this range, all even addresses will go to this memory chip, all odd addresses will go to this memory chip. Right? That is what the memory has been divided. Okay. Now one by one we will see about this. This is RAM 1 even. This is RAM one odd. Okay, we can name these chips. You can name these chips as this particular memory chip is RAM 1 even, this particular memory chip is RAM 1 odd, this is RAM 2 even, RAM 2 odd. So totally how many memory chips we are going to use here? Total six memory chips. Okay, now let us see the memory map of these all 6 chips. Can you see here? ROM even. Okay, ROM 1 even, you can take a ROM 1 even. ROM 1 even, starting from, it is all the even addresses of ROM. ROM 1 odd, all the odd addresses, just now we have seen previously. Okay, now RAM 1 even, RAM 2 even, you can see the addresses which you have seen now. RAM 2 even, RAM 2 odd. Okay, now what's next? Tell me, what next? Tell me. You have to write a table for all these RAMs, yes or no? Right? So you know how to do that because in 8088 microprocessor we already discussed, right? See here, this is your, if you take this is your ROM 1, right? Yes or no? Of course we have divided it into even and odd address. Okay, now this is your RAM 1. This is your RAM 2. So can you write a table for this ROM 1, RAM 1, RAM 2 like you have done it for 8088? It's very simple. You just have to write the starting address and ending address. Yes or no? See here. Write a table. See here. This is the table for ROM 1. What is the ending? What is the starting address of ROM 1? 00000H. What is the ending address of ROM 1? It is 00 H. Right? Of course. A16 here, A17, A16, 17, A18, A19 is not represented here. Why it is not represented? As I have told you in my previous class. Why? Because it's 0, right? Okay? You need not spend time, waste time writing that again. Okay? Now, this is the table for RAM 1, right? This is the table for RAM 1. What is starting address? Ending address is given here. And this is the table for RAM 2. Okay, now what to do with this table? This table is very important because it gives us the entire design of our decoder logic. Next step for this will be design of a decoder logic. Okay, we have already seen about decoder logic in our previous class, right? So what are the things we need to search in this decoder in this particular table? First, see what are the inputs to memory chip, right? What are the inputs to memory chip? Okay, so memory chip requires address, right? Right. So which are the address lines of this 8086 address line will go directly to the address lines of the memory chip? Tell me. See, A0 you cannot use here, right? Can you use A0 here? Can you use A0? Can you see what is the purpose of A0 here? A0 will select 2 banks, right? I told you in my previous class. Here we are going to use 2 memory banks. One is odd address memory bank and even address memory bank. So how can we separate odd address memory bank and even address memory bank? Using A0. Yes or no? Using A0. That's why A0 is used for the selection of 2 banks. Right? Okay. Now you can see that your 2K memory chip requires how many address lines? 11 address lines, right? So you can use A1 to A11. This A1 to A11 can go directly to the address lines of the memory chip to select 2K among every memory chip, right? So now one thing you have done, this is going to select your even and odd bank, right? All, so if you want to separate, because your entire memory is separated into even and odd address bank, right? In 8086. So how does microprocessor differentiates between these 2 memory banks? Using address line A0, right? You can see that A0 is 0 for all, even A0 is 1 for all address, all odd addresses. That separates your even and odd memory banks, right? Okay. and then A1 to A11 will go directly to the address lines of the every memory chip, because every memory chip requires 11 address lines. Now, remaining address lines will go as an input to the decoder logic, right? Where the input to the decoder logic will select these memories. Right, now can you tell me from this table, which are the three address lines, okay? Which are the three address lines, okay? Unique for your ROM1, unique for RAM1, and unique for RAM2, because you need to select either RAM1, RAM2, ROM1, RAM2, RAM3, right? Using the decoder, right? So can you tell me which three address lines, okay, which has unique values in this, okay, which can separate your ROM1, RAM1, RAM2? Can you tell me which are the three lines we can use? You have many options here, right? But you can see A11 and A12, right? Can you check here which are the three lines? Just check. You have to see, already A11 will go for your address lines, right? What are the left? What are the address lines left? Which you can give it as input to the decoder logic? That is A19 to A12, right? So out of this line, there are three inputs has to go the select input of the decoder, right? Which selects your ROM1, RAM1 and RAM2. You tell me which are the three lines you can select in this? Come on. See here, A12, A15, right? A12, A15 is 00 for this, yes or no? See here, right? Now, can you see what is A12, A15 for RAM1? It is 10, right? Yes or no? And then you can see for RAM2, you can see it is 11, yes or no? You got unique lines, right? And then you can select any other line, maybe A16, because it's all 0, right? Yes or no? Right. Suppose if you take A16 is 00, right? Here is 00, it is 00. Now you can see for ROM1, when A16 is 0, A15 is 0, A13 is 0. Sorry, A12 is 0. Okay. And for ROM1, you can see A16 0, A15 0, and A12 0. Yes or no? That means which is the three unique line for selecting ROM1? A16, A15 and A12. Hope you are understanding this. Right here also, can you see here? It is 010. Right. In this case, it is 000. Right. In this case, it is 010. In this case, it is 011. You got it? Select line you got, right? Select line you got, yes or no? Hope all of you are understanding this. Okay. Select line you got. Right, then what else? What you will do with the remaining address lines? What you will do with the A13, A14? What you will do with these three? This can go to the decoder enable lines. Decoder enable lines. Hope you remember that. This will go to decoder enable lines. This can go to decoder enable lines. This will enable the decoder for this particular address. That's all. You're done with your. And then how do you separate even and odd? A0. Right? Your decoder will select your ROM1, RAM1, RAM2. Okay. But in ROM1 you have even and odd, right? Once again. And you have once again RAM1 even and odd. Similarly, RAM2 you have even and odd. Who separates that? A0. You can put just a OR gate and you can separate the even and odd memory. Understood. Now, let us see how do you design our decoder logic. See here. See here. A16, A15, A12, right? It is going as a select input to the decoder logic. Right? Which will separate, Okay, it will select. Okay, so you can say whenever it is 0, 0, 0, which line will get activated? ROM 1, right? ROM 1. So this is the activation line for the ROM 1. Understood this? Okay. Now for RAM 1, you have seen 0, 1, 0, right? When it is 0, 1, 0, it is RAM 1. So this line is going for RAM 1. Of course, in ROM 1, there is even and odd. You will separate that. Okay. Now, when it is 0, 1, 1, RAM 2, right? So this connection is for RAM 2. See. So this A16, A15 and A12 will select ROM 1, RAM 1 and RAM 2. Right? This will select that. Okay. And how do you select this chip for this address? Using remaining address lines. What are the remaining address lines? A13, A14. Right? All are permanently 0, right? For entire address range, all are permanently 0. Right? That means this G2A and G2B require always 0, right? Yes or no? So you connect your A13, A14 to G2A and G2B, which is permanently 0, which is required for this decoder chip. Similarly, remaining lines are also 0, right? You connect it to a NOR gate and give permanent 1 to this, yes or no? Your entire address range of ROM 1, RAM 1 and RAM 2, you can see these lines are always 0, right? Right? So whenever any address generated by microprocessor in that range, this will be always 0. So this will give 1 here, which is required to select this particular chip. Right? Now come to this side. Come to this side. Now ROM 1. In ROM 1, you have both even address and odd address, right? But separate, right? Separate, yes or no? But separate. So how do you separate? See here. You connect this, be careful, you connect this to a OR gate, okay? You connect this to the OR gate, see here, and another input to this OR gate is coming from A0. Can you see this is A0 line? Right, A0 line, right? See, it is something like this, just see here, something like this. This is the selection of ROM 1, okay? ROM 1 will be selected, right? Once again, ROM 1, you have to separate, the signal has to be separated into 2 chips, right? See, ROM 1 is divided into even number, even odd bank and odd bank, right? Now, the chips is different. You have 2 chips connected to here. See here, you have 2 chips connected. This is a 2K chip, which is ROM 1 even. Try to understand this. There is another chip, also 2K, which is ROM 1 odd. Right? Now, ROM 1 is selected from the decoder. But how do you select these 2 chips? You can use address line A0 and bus high enable. Right? Now see. Now ROM 1 is selected. Give this to a OR gate. OR gate. Give this to a OR gate. See here. I'm giving this also as the one of the input to OR gate. Okay. So this is going to select this 2K ROM. Okay. This is connected to chip select of this. This is connected to chip select of this. Right? Now you see, whenever your even banks are selected, even addresses are selected, it will be selected to A0, right? Yes or no? What is required to select this is chip select bar. A0 will be always 0 for all even addresses, right? Yes or no? So you'll get 0 here. And ROM 1 selected means you will also get 0 here. Yes or no? Is active high, active low input. Your decoder output is active low. So selection of ROM 1 will give you 0 here. 0 OR gate 0 will give you 0 here. Yes or no? And this will be selected. Right? During odd addresses, Can you see during odd addresses A0 is 1, right? Is this chip selected anytime during odd addresses? Come on, think. Why this chip is not selected during odd addresses? A0 will be 1, right? For all odd addresses, A0 will be 1. Since A0 will be 1, this chip will not be selected. This chip will be selected only when A0 is 0. Now, can you tell me what I should connect here for this particular chip? Bus high enable. So whenever odd address is generated, your bus high enable, that is, it is trying to put the higher byte of the data. The higher byte of the data will be put when your bus high enable is low. See, for odd addresses, your bus high enable will be 0. Okay, and your ROM1 selection is also coming 0 here, and this will get 0. Odd bank will be selected. Odd bank will be selected. Have you understood now how microprocessor selects even and odd address banks? Right? So A0, now can you tell me when A0 is 0 for all even addresses, right? Now, is this BHE becomes 0 anytime during even addresses? No. This BHE will remain 1 whenever even address is generated. Only when odd address is generated, this BHE will become 0. And when odd address is generated, this will become 1. Yes or no? So you will be able to separate your ROM or RAM into even address and odd addresses because of this. Right? Now, same thing for RAM. RAM will be selected, and A0 and bus high enable will select RAM 1 even and RAM 1 odd. Similarly, RAM 2 will be selected by these three address lines. Once again, RAM 2 will have even address bank and odd address banks. That will be separated through bus high enable and A0. This is the way you have to design a decoder logic for this whatever specification given to you. This is the final step. If you have done this correct, almost you will get 95% of the marks. Okay, finally, you may be, if you have time, you can write this diagram. Can you see here? A complete diagram. Same thing. It is same thing what we have seen earlier. Okay, see here. What is this? See, these are the signals coming from microprocessor. Signals coming from microprocessor is A0 to A19. You have D0 to D15. You have write bar. You have read bar. Okay, and you have bus high enable. All those things. Okay, now see here. Out of A0 to A19, okay, A1 to A11 will directly go to memory chip, yes or no? These are the memory chips. You have 6 memory chips. See, listen carefully. 6 memory chips. Out of that, 3 will be holding all even addresses and 3 will be holding all odd addresses. Okay, right? But you have the common address line going for all like 2K memory chips, because 2K memory chips requires 11 address lines. Okay, so that means A11 to A1 to A11 will go to all the memory chips, right? So this is your this is your odd memory bank because bus high enable is connected. This is your even memory bank. See here, it's the same decoder logic. Same decoder logic you have seen. See, A13, A14 goes to this, right? And you have these 3 address lines, A19, A17, A18, A19 going to the G1, right? It's giving 1 here. This is giving permanently 1 here. This is giving permanently 0 here. Okay. Now what are these 3 lines? These 3 lines select lines, right? A12, A15, A16 will select your output. Yes or no? So 0, 0, 0 will select what? It will select. It will select ROM. Okay, 0. It will make 0 active, right? Active low. This is ROM 1. Then this will select ROM 2. This will select ROM 3. Right. Now, see here. ROM 1, ROM 2, ROM 3, all odd. ROM 1, RAM 1, RAM 2, all even addresses. So, can you tell me which is separating even and odd? See carefully. ROM 1, see, this is ROM 1, This is your ROM 1, okay? Now see ROM, this is RAM 2, sorry, RAM 1, sorry, RAM 1, RAM 2, RAM 1, see this is RAM 1, can you see? It's going through this, this is your, this particular chip is RAM 1. What is this chip? RAM 2. And all these are even. Why even? Because another input to this OR gate is given, sorry, odd, this is odd, because bus I enable is given here. Okay, so all these are odd chips because bus I enable will activate this. Similarly, see, same line is coming here. So this will be what? Tell me. This will be ROM 1, this will be RAM 1, this will be, last will be RAM 2. And you can see A0 is given as a common to all the OR gates here. So this is the final memory design for 8086 microprocessor for the given specification, Have you understood this? Okay. So this is the final result. That's all. Designs. Okay. But you need to practice this. It's very important. Everyone need to practice this. Now, let us take one more example. Okay. Try to understand it clearly. Now, what is required? Tell me now. How much memory we need to interface? You need to interface 1 mega RAM to 8086 microprocessor. Chip available is 256K. Okay. Now, what is the first work you have to do in this? You have to get a memory tree. Yes or no? Yes. Okay. So first write 1 megabyte, divide it into 512K. Okay. You odd and even will come moment you divide, whatever division you do, reach to the memory chips available. Don't take, do you have to take even and odd here? Now next division, this will be even, this will be odd, this will be even, this will be odd. Don't make even and odd here. Don't make entire 1 MB coming to be 512 even and 512 odd. Don't do that. Why? Because the chips available is 256K, right? That only can become even and odd. 512 chip is not available. That's why once you divide this 512K once again in the tree, now this is 256, right? This is 256. This is 256. This is 256. Now you take this as even of this, odd of this. Even of this, odd of this. Can you tell me what is the address range for this? Come on, fast. What is the address range for this? 1 MB. Come on, all of you know about it. What is the address range for this? 1 MB. Come on, it is FFFFH, right? Entire address range, right? Okay, now what is the address range for this? 0, 7. Okay, what is the address range of this? 0, 08. Yes. FFFF. So now, out of this, all even will come to this, all odd will come to this, okay? In this address range, all even will come here, all odd will come here. What's the next step, tell me? This is your RAM 1, yes or no? This is your RAM 2. This is your RAM 1. This is your RAM 1. This is your RAM 2. Okay, this is your RAM 1 even, RAM 1 odd, RAM 1 even, RAM 1 odd. Okay, what is the next step now? Table. You make a table. Now. See here. This is the table. Now tell me, what are the things getting changed here? Now tell me, you can just decide your entire, this is the table, right? This table is for, this is for RAM 1, right? This is for RAM 1, yes or no? And this is for RAM 2. Okay, now can you tell me how we are going to design? Because here, how many address lines goes directly into the address line of the memory chip? A0 to A0. Right, you can see A0 to A18. That means how many address lines are required for you to address 512 256 KB of memory? Right, your memory chips are of size 256K, right? So how many address lines are required to address 256K memory? Is it 18? Just check. Is it 18? 18. That is A0 to A17. So A0 to A17.
Sir, A0 is equal to
Definitely. Yes. Yes. True. That's true. Okay. Exactly. See, this you may have multiple options for that. Okay. Suppose if you take A0 for even and odd, okay, right? A0 will separate this 512K as a even bank and odd bank, okay? Similarly, you can see your A0 here will separate another RAM to even and odd, okay? Now, how many address lines can go directly to the 256K memory chip? A0 has gone. 18. A1 to A1 to 18, right? So A1 to A18, this entire address lines will go directly into the memory chip. Then what else left for your input to the decoder logic? Only A19 left. You can see that your A19 is all 0 for RAM 1 and your A19 is all 1 for RAM 2. Use this remaining line, you can directly graph it, right? You can go for incremental addressing model this. Okay. Now you see here.
again. How you get A1 to A18?
The memory chips which are used is 256K, right?
Yes, sir.
How many address lines are required for this memory chip? How many address lines are required for 256? Calculate. You require 17 address lines, right? Yes or no? 17 or 18. You need 18 address lines, right? And from where you're going to take that, from your A0 to A19 or from microprocessor? From A1 to A18, yes or no? Because A0, you can take A0 to A17, but A0 is going for your even and odd selection. A0 is going for your even and odd selection. In that case, you can use the remaining lines. You can use A1 to A18. You have that option. Understood? Remaining line is going for your decoder logic. And decoder logic, you can see that A19 is actually, it is 0, 0, 1, 1. Okay? You can do like this. Right? You can ask me, sir, what about your G1, what about your G1, G2A, G2B and all? Right? You can directly ground that, no problem. Right? What is required is only A19, right?
Yes.
This is 0, 0, 0, 0, 0, 1. So A19 will select, this is your RAM 1, this is your RAM 2, right? Yes or no? So A19, what about your G1? G1 requires 1, right?
Yes.
Right, you can directly connect it to VCC. Now similarly, you can see here, you can ground this, and bus enable is always 0, right? You can even ground this one also, doesn't matter. Both you can ground. Right, now can you see here, can you see here, See, one option to do this is using two decoders. See, this design can be done using two decoders. Okay. This decoder will be selected whenever bus enable is 0. Okay. Now, this decoder will be selected whenever A0 is 0. That means this decoder is for odd addresses and this decoder is for even addresses. See, you have the option to use two decoders. Depending on the design, you have the option to use two decoders. Okay. Now, can you tell me how to do this same problem with using one decoder? I want to convert this. Of course, see, here we are using two decoders. Okay. See, one of the decoder G1 is given as bus enable here. One of the decoder is given, the select input is given as A0 here, right? And you know, whenever for all even addresses, A0 will be 0, right? Right. So this decoder will be selected. A19 is connected to this. So this all memory are nothing but even address memory bank. And this one, this is odd because for this decoder, you have connected bus enable. I have understood this. Now, depending on my just previous topic, can you convert this entire diagram using only one decoder? Only one decoder. How to convert this into one decoder? Tell me.
Okay.
Exactly. Right? But what to do with this bus enable? Directly ground this. I've understood. Directly ground this. Okay? This will not be there at all. Right? Then you do the same arrangement using OR gate. I've understood this. Okay? So I will draw this once again here. See. I will draw this once again here. This is your decoder, okay? A, B, C, okay? This is your G1, G2, this is, you ground this. And connect your G, this is G2, G2A, G2B, G1. You connect this to VCC. Right? This is your A19. These two are grounded. I've understood this. Now, what is selected is 0, RAM 1, and it is 1, RAM 2. Now this RAM 1 once again, come on, tell me, two OR gates, and this is, one is connected to even, one is connected to odd. So for odd, another input is coming from bus enable. For even, another input is coming from AC. That's all. This is making use of only one decoder. But what is shown here is making use of decoder. Right? So this decoder will be selected whenever bus enable is 0. This decoder is selected whenever A0 is 0. The different ways of doing this. In the question, if it is asked to use only one decoder, don't go for this type of design. Okay? In the question, if it is asked, you can use any number of decoders, go this type of design. Have understood this? Okay? Now, we will do some more problems based on this. Okay? Now, can you do this? Can you do this? Start doing this. Now, you have to interface 16K of RAM, 16K of RAM to 8086 microprocessor, starting at address 0000H. What are the chips available? Chips available is 2 KB, right? And 4 KB. See, this is very, very interesting here, right? So now you are going to design. See, there are 4 chips of 2 KB available, 2 chips of 4 KB available. Have understood this? Now, how are we going to divide this? division of the memory division is very important for this. Okay, simple division is okay. Okay, suppose if you have been asked to design 16 KB of RAM and chip given is only 2 KB, for example. So how will you divide that? Right, see, 16 will be divided into 8 and 8. This will be once again divided into 4 and 4, and this 4 is divided into once again. This is even, odd, even, odd, even, odd, even, odd. All are 2 KB, 2 KB. This is fine, right? This is very easy. Suppose if it is told that you have been given 4 chips of 2 KB and 2 chips of 4 KB. How can you do this? It's very simple. 16 is divided into 8K, 8K, right? When you divide this can be divided into even and odd, right? This is 4 even, 4 KB even, 4 KB odd, right? And this 8K, once again divide into 2 4Ks. 2 4Ks, yes or no? Don't make it even and odd, because available 4K is only 2. Now this once again divide into 2K even, 2K odd, 2K even, 2K odd. Done. Now you put the address range. Address range, starting address is 0000H. You know how to put the ending address, right? You know how to put the starting address and ending address for this. You know how to put starting ending address. Here starting ending is not required. Why? Because whatever range you are getting here, out of that even will come here, odd will come here. Now once again you get the starting and ending address of this, starting ending address of this, and these two will be held in even and odd, right? So this will be, now you can name it something like this. Okay, I will divide this as, see here is RAM 1, RAM 2, this will be RAM 3. So what will be this? RAM 3 even, RAM 3 odd. This will be RAM 1 even, RAM 1 odd, RAM 2 even. Can you just write the address range of this when you come to the next class? I'm going to continue from here. Can you write entire address range for all the chips? See, this is the address range for all the chips, right? RAM 1 even, RAM 1 odd, RAM 2 even, RAM 2 odd. See, this is your 2K, 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 but this is 4K, this is 4K. I've understood this. See, this is your RAM 1, this is your RAM 2, this is your RAM 3. Okay, RAM 1 even and odd, RAM 2 even and odd, RAM 3 even and odd. What's the next step? Okay, tell me. Write the table, come on. Write the table for RAM 1, this is RAM 1, RAM 2, RAM 3. In that table, we select a unique line that your decoder can separate your RAM 1, RAM 2, RAM 3. Right? So selecting even and odd within RAM 1 can be done using A0 and bus enable, connecting simple OR gates. Have understood this? Okay, that's a step. See, I will write the next step, table. Okay? Right, now here there is something. Which lines to go for address lines directly? Here there are 2 memory chips, right? Here you have one memory chip is 4K, another memory chip is 2K. But 2K requires how many memory chips? Sorry, 2K requires how many address lines? 11. But 4K requires 12. Right. So now mismatch, right? Okay. So you can, what you can do is, you can select, your A0 as even and odd as usual. So remaining lines will go to your address lines directly. Okay. And then whatever remaining after address lines, you take it as a decoder select inputs. Okay. And if at all you are remained with any address lines, take it as a enable input to the decoder. Okay. This table is very important. So just tell me, have you understood reaching this table at least now, as of today? Right? After this table, only you have to think, you have to spend some time, right? Out of these address lines, which line will go to the address lines of the chip, right? And which line will select even and odd, which line is given as a select input to the decoder, and which lines are given as an enable input to the decoder, right? Once you have understood, identified those things, next is just connecting that. That's all. That's the end of this particular design. Okay, so just think about it. We will just see this in the next class. We'll continue in the next class for this. Okay, just answer your numbers. Okay, Hisham. Hisham. Okay, you are coming after many days. Aditya. Prakriti sir. Niti. Larissa. Marvin. Hitesh.
Yes, sir.
Zubair. Mubashir. Naganandan. Johan Girish.
Yes, sir.
Sinan, Mohammed Sinan. Dahlia Patel.
Present, sir.
Vivek.
Yes, sir.
Alex.
Sir.
Nimish. Aryan.
Sir.
Aryan Ramabhadran. Dharma. Saini Suraj. Absent. Kailash.
Yes, sir.
Naina Siklani. Syed Abdullah. Paridhi. Jaskaran Singh. Murthy.
Present, sir.
Malvika. Absent. Aryan.
Present.
Amit. Tanish. Absent. Vishnu Purai. Rajdeep.
Yes, sir.
Rishikesh.
Yes, sir.
Ameya. Rishikesh.
Sir.
Shafi Muhammad.
Sir.
Prathamesh. Venkat. Suleiman. Prakar Singh. Ajit. Ranivi Ajit. Ishan Kurian. Yes, sir. Varshita. Mustafa.
Yes, sir.
Mohammed Shifa. Munib Ahmad.
Yes, sir.
Muthurity. Ved.
Yes, sir.
Sai Shri. Lynn.
Yes, sir.
Uday Singh. Bhumi. Yashita. Why people are absent? Ashish. Okay. Rais Ahmad absent. Rishil present. Sarashwan. Par. How many absence? God. Ratik. Nupur. Nikita. Sofana. Zahid Muhammad. Saransh.
Present, sir.
Harshit.
Yes, sir.
Radhika. Absent. Varnika. Ashwin.
Present.
Sneha. Sania. Nihal.
Yes, sir.
Okay, we will continue from this class. I'm going to share this video with you.